All right. Good morning, everybody. Welcome back. So today, let's try to finish chapter number 4. And as I told you last week, the recording will be available if you want to watch the lecture later. The link will be posted on Canvas. Okay. All right. So let's start the screen share, and I have some quick announcements to make. So let's start with that. Okay, some important announcements here for this week. Attention with the online homeworks. For next Monday, you have two uh, homeworks that are due, Chapter 3, Part 2, and Chapter 4, Part 1. Okay, so do not leave for the last minute, please. Okay? Try to break up the homework in small parts, and that will give you a better chance. And we will have in-class assignment this coming Thursday, 10:15. Okay, with that being said, so let's pick up where we left. So we are talking about acid-base reactions. When you combine an acid and a base, the products will always be a salt and water. And the salt formed may be soluble or insoluble. Okay, and you will know if the solid is insoluble by looking at the solubility tables. We also saw last week that two salts may combine and also yield a precipitate. Okay? So the example that I gave you was the reaction between lead nitrate and sodium iodide. So we wrote all the equations, and that will yield this beautiful yellow solid here. And the identity of the solid is lead iodide. Okay, so let's move on with chapter number 4. And I would like to wrap up the reactions and just saying that precipitation is a very efficient way to quantify determined ion in solution. And it's a very efficient way also to remove an undesirable contaminant from the environment. Uh, the classic reaction here is the removal of calcium ions from water. If we have excess of calcium in the water will look cloudy and it will give the impression that it's dirty. And also calcium will accumulate in the pipes and eventually will clog the pipes. Okay, so excess of calcium in water will give uh, the origin to something called hard water. Therefore, calcium needs to be removed, and that's what we do in the water treatment plants, is removal of calcium ions, of excessive calcium ions. And that's a very simple reaction where you will precipitate calcium ions by the addition of aluminum sulfate or even sodium carbonate. Okay, when aluminum sulfate is added, calcium is going to combine with the sulfate because that's the negative part of the salt and will precipitate as calcium sulfate. Once calcium is precipitated, you can filter or decant and get rid of the calcium. And the other way is by adding sodium carbonate. Again, calcium will combine with carbonate, forming calcium carbonate. This salt is insoluble, that will precipitate, forming a solid, and again, can filter or decant and get rid of the calcium. Okay, so that's an example of a practical use of a precipitation reaction. Okay, so we are always looking to precipitate something because it's just easier to separate from the rest of the solution. Okay, so at this point, I would like to start a new topic. So we will talk about oxidation reduction reactions, or also called redox reactions. So there is a very neat experiment, and it's a shame that I cannot show you live. But if we have magnesium strips and we put fire on them, they will burn and produce a very bright, beautiful white light. And the result of this reaction is the formation of magnesium oxide. Okay? As I told you before, any chemical reaction involves the rearrangement of the atoms. Atoms cannot be created or destructed. Okay? Always combine, always changing the way that they combine. And the same is true for electrons. Any chemical reaction involves the transfer of electrons. Electrons cannot be created or destructed, only transferred. Attention with that. Any chemical reaction will involve an element losing electrons and another element gaining electrons. And that's our focus on oxidation reduction reactions. So we will estimate how many electrons were lost by an element and how many electrons were gained by the other element. Remember, an element that lost electrons becomes positive, while an element that gains electrons become negative. Okay, careful with that. This has to be clear in your head. Okay, so our goal is going to be to determine how many electrons were gained and lost by each element. To do that, we are going to use something called oxidation number. Oxidation number is a sort of measurement to indicate to how many electrons were lost and how many electrons were gained when two elements combine. So now it's a good time to change my screen to my iPad so I can write. All right, so let's start to talk about oxidation number. And again, oxidation number, or also called oxidation state of an element, give us an idea of how many electrons this element lost or gained. Okay, so the idea behind that is every time that two elements combine, let's call here A and B, and there is a pair of electrons shared. So I'm going to represent this pair of electrons shared by this horizontal line. Sometimes one of the elements gain electrons and the other one loses electrons. So A and B are always fighting to get the electrons close to each other. And that's what the oxidation number will sort of measure. And just reinforcing here that if the oxidation number is negative, the element gained electrons. Okay, there is an excess of negative charges. On the other hand, if the oxidation number is positive, this element lost electrons. Okay, or there is excess of positive charges. Okay, to determine the oxidation number, there are a set of rules that we must follow and that will guide us to get all the oxidation numbers from all the compounds involved uh, in the formation of a chemical compound. So let's start with the rule number 1. Each atom in a pure element has an oxidation number of 0. Let's give here the example of Br2. Okay, when I write Br2, that means we have 2 bromine atoms that are sharing a pair of electrons. Again, I'm representing here the pair of electrons shared by this horizontal line. You may also see the Lewis representation being right like that. And that means that this pair of electrons is shared. Okay, so let's write here, shared pair of electrons. Always the chemical elements will try to pull the electrons close to them. So it's a battle for the pair of electrons. But let's think here together. If we have 2 people pulling to opposite directions with the same intensity, nothing will move. So that means this pair of electrons is right in the center. So it's not close to the Br on the left and not close to the Br on the right side, which means nobody is gaining and nobody is losing. Therefore, the oxidation number for each bromine is 0. And we are going to represent that as a number on the top right corner of the element. Okay? So every time you have a compound that's formed by the same element, that means the oxidation number is 0. And we will represent that by Br2, and you can put a 0 here. Okay, so here that means oxidation number or oxidation state. All right, moving on here, let's move on to the second rule. The second rule says that the sum of the oxidation number of the atoms in a neutral molecule is 0, unless the ion is charged. So that means when we have 2 atoms combining and the atoms are from different elements, someone will lose electrons and someone will gain electrons. Okay, so the term here, losing and gaining, means that who lost the electrons means that the electrons are far from this element, and who gained the electrons has them close uh, to it. Okay, so let's take a look here at 2 examples. Let's start with CO2. If there is no number outside the compound, Okay, so no number right here. That means the sum of the oxidation states of the elements in this compound has to be 0. Okay, so again, if there is no number on the top right corner outside of the compound, that means the sum of the oxidation number of the atoms has to be 0. Therefore, if we sum the oxidation number for the carbon plus 2 times the oxidation number for the oxygen, this has to be 0. Okay, so that means someone lost electrons, and those electrons that are lost are going to someone else. However, if there is a number outside of the compound on the top right corner, that means the sum of the oxidation numbers has to be equals to that number. Let's take here as an example carbonate. For the carbonate, we have a number outside here on the top right corner. What this number is telling you is that the sum of the oxidation numbers has to be equals to that number. Okay? So, in other words, if I add the oxidation number for carbon plus 3 times the oxidation number of oxygen, this has to be minus 2. Be very careful, okay? Every time you have a number outside of the compound, that indicates the sum of the oxidation numbers of each atom has to be equals to that number. Do not forget about the sign of the number, because that's going to be important. Okay, you have to consider the sign outside. Okay, rule number 3. Hydrogen is usually very weak, and that means the oxidation number of hydrogen is always 1 plus. When combined to a different element, except in metal hydrides. In the case of metal hydrides, the oxidation number of hydrogen is 1 minus. What is a metal hydride? Metal hydride is any compound formed by a metal plus hydrogen. And metal here can be any element that belongs to the groups 1 all the way to the group 13. Okay, so that's when we have metal hydride. For example, sodium hydride. This is a metal hydride because sodium is from the group 1. Or for example here, aluminum hydride, AlH3, that's also a metal hydride. And in these cases, the oxidation number of hydrogen is 1 minus. For all the other cases, the oxidation number of hydrogen is 1 plus. When combined with an element that's not hydrogen, of course. So let's see how that works in the HCl compound. Okay, so let's try to give you this example here. Okay, HCl. Okay, our goal here is to determine the oxidation number or the oxidation states for all the elements that are uh, in the compound. So let's start here with rule number 2. Rule number 2 states that the sum of the oxidation states is always 0 unless indicated. Remember, every time there is no number outside of the compound, that means the sum of the oxidation numbers is 0. So if we add the oxidation number of hydrogen plus the oxidation number of chlorine, this has to be 0. So let's write that. Let me write here oxidation number of hydrogen plus oxidation number of chlorine. This has to be 0 because there is nothing indicating that the compound is charged. The oxidation number of hydrogen is always 1 plus. So let's replace that in the equation. So let's put here plus 1 plus the oxidation number of chlorine. This has to be 0. What's the only number possible for the oxidation number of chlorine? 1 will move to the other side, changing the sign. Therefore, the oxidation number for chlorine is equals to minus 1 or 1 minus. Doesn't matter here. Okay, so what's the physical sense of this number? What does this number tell us? Hydrogen chloride is a covalent compound. So that means there is a pair of electrons being shared. And because the oxidation number of chlorine is 1 minus, that means the chlorine gained electrons. And it's the opposite for the hydrogen. The hydrogen lost electrons. So if we could take a picture of this chemical bond, we would see the pair of electrons closer to the chlorine and farther from the oxygen. That is the meaning of an oxidation number of 1 minus and an oxidation number of 1 plus. Okay? Remember, there is always a battle for the electrons. Some elements like to lose the battle, and some elements like to gain the battle. And that's a property of each element that we will see later, and it's called electronegativity. Okay, so hydrogen always like to lose the battle. So the oxidation state of hydrogen is 1 plus, except in metal hydrides and except when combined with another hydrogen. And that's the rule number 3. Now I would like to move on to the rule number 4. The oxidation number of oxygen is usually 2 minus, except in peroxide compounds where it is 1 minus. Okay. What is a peroxide compound? Peroxide compound is any compound that has oxygen bonded with oxygen and then bonded to another element in the extremes. One example of a peroxide that everybody knows is the HOOH. That's also called hydrogen peroxide. And the formula is H2O2. Okay? And in this case, this is the only case that the oxygen has oxidation number equals to 1 minus. And I will tell you when you have a peroxide. Okay, so you don't need to know at this point. So this is the exception. So now let's move on to the rule. The rule says that usually oxygen has oxidation number equals to 2 minus. So let's see how that works and how that helps to determine the oxidation number for other elements in a compound. Let's go back to the CO2 example. Again, remember that if there is no number outside of the formula of the compound on the top right corner, that means the sum of the oxidation numbers is equals to 0. So let's write that here. So we know that the sum has to be 0. And we know that we have here the oxidation number of the carbon plus, attention here, because we have 2 oxygens, therefore we have to multiply by 2 the oxidation number of oxygen, and that has to be equals to 0. Okay, so be very careful with that. You have to multiply the oxidation number by the number of atoms. Okay, so let's continue here. We know the oxidation number of the compound, which is 0. We do not know the oxidation number of the carbon, but we know the oxidation number of oxygen. The oxidation number of oxygen is going to be 2 minus every time that oxygen is combined to another element. So let's replace here 2 times minus 2. Careful with the sign again. Do not forget it. This has to be equals to 0. Let's move everything to the top here. So let's rewrite here oxidation number of the carbon plus 2 times minus 2, that's minus 4, has to be equals to 0. There is only one solution for this equation, so I'm going to move minus 4 to the other side, and that will change the sign. Therefore, the oxidation number of the carbon is equals to plus 4 or 4 plus. Okay, doesn't matter here. So that means when carbon combines with oxygen, that basically tells you that carbon lost 4 electrons in this chemical bond. And oxygen gained the 4 electrons. Okay, so every time someone loses, someone has to gain it. What's the physical meaning of that? Doesn't matter at this point how I got to this structure, but CO2 has this structure represented over here. So each dot represents an electrons, and we have 4 pair of electrons being shared. And if we could take a picture of these electrons, that would mean that they are super close to the oxygens and far from the carbon. And that's the meaning of an oxidation number of 4 plus and an oxidation number of 2 minus. Okay. The meaning is that the electrons are closer to the oxygen and farther from the carbon. So oxygen, for some reason, likes to pull the electrons closer. Another element that likes to get closer to the electrons, likes to pull electrons, is fluorine. Fluorine has always oxidation number equals to 1 minus in any compound except F2, except when combined with itself. Okay, so any element that combines with fluorine will lose the battle for the electrons. So fluorine is the strongest element when we talk about pulling electrons. And later on, I will tell you that fluorine is the most electronegative element in the periodic table. And knowing that, that will help us to find the oxidation number of the other elements. So let's take here the example for the CF4 compound. So let's rewrite here, CF4. Again, if there is no number outside of the compound on the top right corner, that means the sum of the oxidation numbers is equals to 0. So that's the first thing we will write. We know that this compound is formed by 1 carbon and 4 fluorines. So let's write that. And we know that the sum of the oxidation numbers has to be 0. So I'm going to write here oxidation number for the carbon plus 4 times the oxidation number of the fluorine has to be 0. Again, where did I get the 4? Because we have 4 atoms of fluorine, we have to multiply the oxidation number by 4. Okay. What we know and what we don't know here. We have no idea about the oxidation number of the carbon. So let's rewrite here. We know that fluorine, when combined with a different element, has always oxidation number equals to 1 minus. So let's replace that. So I'm going to write here -1. and that has to be equals to 0 because the compound is not charged. Oxidation number of the carbon plus 4 times minus 1 is minus 4 equals to 0. There is only one solution for this equation, and that means the oxidation number for the carbon is equals to plus 4. Okay? So usually carbon will lose the battle for electrons, usually, okay? And it was a coincidence here that example 4 and 5 gave the same number for the oxidation number of carbon, okay? But sometimes that's not the truth. And again, what's the meaning of an oxidation number equals to 4? So you don't need to know that now, but CF4 has this structure that I'm showing here. Each dot means an electron, and each bond means that a pair of electrons is being shared. If we could take a picture of the electrons in this compound and the position of them, we would see the pair of electrons much closer to the fluorine than the carbon, because the oxidation number for fluorine is 1 minus, okay? And the meaning of that is that fluorine likes to pull the electrons close to it when there is a covalent bond. And that's the meaning here of the charge 4 plus and the charge 1 minus for each fluorine, okay? And the final rule is that elements from the group 1, when combined, have oxidation number 1 plus. That's going to be always the case. And elements from group 2, when combined, have oxidation number 2 plus. So group 1 always going to have oxidation number 1 plus or plus 1, and group 2 always 2 plus or plus 2. All right? So those elements will not put in a battle for the electrons. They will just give up and be happy with that. Any questions so far? Okay. If there are no questions, the best way to learn oxidation numbers is by practicing. So let's try to determine the oxidation number of the elements in bold. Okay, so the first one is chlorine, second one is also chlorine, and the third one is sulfur. Let's use all the rules that I showed you, and let's see if we can do that together. Okay, so this is a good point for us to take a break. Let's take a 5 minute break, and I will be back at 11:46, and then let's solve together and let's see if we got the right result. Okay, so 5 minute break. Let's resume at 11:46. Okay, so let's go back here and let's determine the oxidation number of the elements in bold. Okay, so let's do that together. Let's see if you got it right or if we need to explain things better here. So let's start with ClO2. Okay, what I like to do, you don't have to follow what I'm doing, but what I like to do is to rewrite the formula of the compound. Always check if there is a charge or not. If there is no number outside here, that means the sum of the oxidation numbers has to be 0. So let's write here, and let's put a sign, an equal sign here, meaning that the sum has to be 0. Okay, now let's write that the sum of the oxidation numbers for all the elements in the formula is 0. Starting here with chlorine. So oxidation number of chlorine plus 2 times the oxidation number of oxygen is equals to 0. Okay. Remember that because we have 2 atoms of oxygen, you have to multiply the oxidation number by 2. Okay. Do not forget about that. So let's move on this up here. We don't know the oxidation number of chlorine. So that's what we want to find. So let's rewrite here. We know that oxidation number of oxygen is always 2 minus if this is not a peroxide, and this is not a peroxide. So let's write here 2 times minus 2. That has to be equals to 0. Therefore, oxidation number of chlorine plus, attention here, do not forget the sign, plus minus 4 equals to 0. There is only one solution for this equation, and the solution is that oxidation number of chlorine is equals to plus 4, or if you want to write 4 plus, that's also correct. Okay, and that's how you determine the oxidation number for the elements in a compound. The 4 plus means that chlorine, when combined with oxygen in this compound, lost 4 electrons and oxygen gained 4. Okay. Remember, there is always a battle for the electrons. Some elements like to keep the electrons closer, and some elements are not strong enough to keep them closer. Okay, let's move on to the second example here. Uh, Pay attention to the second example because there is a different thing. So we have here ClO4, ClO4, and this time there is a negative charge outside of the compound, okay, right here. And that means, in this case, the sum of the oxidation numbers has to be equals to the charge. So what I like to do is to write that the first thing, so minus 1, and that has to be equals to the sum of the individual oxidation numbers. So let's write here oxidation number of chlorine plus 4 times the oxidation number of oxygen. Again, there is a 4 there because we have 4 atoms of oxygen. Therefore, you have to multiply the oxidation number by 4. Let's move on this over here. Let's replace what we know and let's leave what we don't know. The goal here is to determine the oxidation number of chlorine, and we know that the oxidation number of oxygen is -2. And
That's from rule number 4, right?
yes,
Okay, okay.
yes, yes. And attention here, because now there is a charge outside of the compound, the sum has to be -1. Okay? Always follow the rules, and that will lead you to the correct answer. Okay. Oxidation number of chlorine, that's what we are looking for, plus 4 times -2, that's -8, equals to -1. There is only one solution for this problem. Very careful here with the signs. -8 will move to the other side as +8. +8 minus 1, oh, sorry about that, is +7. Okay? So the oxidation number of chlorine in this compound is +7, a really, really high oxidation number, because it's combined with 4 oxygens, and oxygen will usually drain the electrons. Okay? So the meaning of this number is that the electrons are far from the chlorine and closer to the oxygen. Okay. Last example, ion sulfate. Again, sulfate is a charged ion, and the charge is 2 minus or -2, so that will be important. So what I like to do is to rewrite the elements and rewrite the charge here. First thing is to look at the charge, and that will tell us that the sum of the oxidation numbers for each element is equals to 2 minus or -2. So let's write that. The sum of the oxidation numbers is -2. And this has to be equals to the oxidation number for sulfur plus 4 times the oxidation number for oxygen. Again, the 4 is there because we have 4 atoms of oxygen. Therefore, we have to multiply the oxidation number by 4. We don't know the oxidation number of sulfur. We know that the oxidation number of oxygen is -2. And we know that the sum of the oxidation numbers has to be -2 because that's the charge of the ion. Let's move our equation up here. So we will end up with oxidation number of sulfur plus minus 8 equals to minus 2. There is only one solution for this equation. Therefore, oxidation number of sulfur has to be plus 6. The physical meaning for oxidation number equals to plus 6 is that the electrons are far from the sulfur and closer to the oxygen. Okay, so technically sulfur lost 6 electrons in the bonding with the 4 oxygens. Okay, there is not a lot of secret here to determine the oxidation numbers. You just have to have the rules clear in your head, and don't forget about signs and small things like that. Okay, and don't rush. Okay, think about what you are doing. And again, the best thing to learn that is by practicing, and that's what we are going to do. Okay, any questions to this point? All right, so if there are no questions, so let's move on. And you can use oxidation numbers to balance a reaction. And this is called balancing reactions using the redox method. And the principle here that we are going to use is that first, the number of atoms before and after has to be the same. Atoms cannot be created or destructed. And also, the number of electrons lost and gained has to be the same. If someone is losing electrons, someone has to gain those electrons. Okay, they cannot be lost. So there is always going to be someone losing and someone gaining electrons. So the first thing I would like to do is to determine the oxidation numbers for all the elements here in the equation. So let's do that using all the 6 rules. And then we will analyze what's going on here. Do you want to try first, or do you want me to just do it and then you try to catch up? All right, if there are no anything against it, so let's do it and let's see what happens here. Okay, so let's start with calcium phosphate. That's the first element in the equation. So let me rewrite here. Calcium phosphate is neutral. That means the sum of the oxidation numbers of all the elements in this compound is 0. We have here 3 atoms of calcium, therefore 3 times the oxidation number for calcium. If we go back to the rule number 6, oxidation number of elements from group 2 is always 2 plus. So we will replace here by plus 2 plus, careful here, okay? We have 2 times the phosphorus, and we don't know the oxidation number of phosphorus. Let's write here. This 2 here has to multiply the elements inside the parentheses. And we have 8 atoms of oxygen. Okay, be very careful. Don't forget to multiply the number outside of the parentheses by the number of atoms. And we know that oxygen is always -2 unless the compound is a peroxide. And this has to be 0. Therefore, the oxidation number of phosphorus, I'm going to jump steps here. And according to my calculations here, it has to be +5. Okay, so let me write here at the top the oxidation numbers. So 2 plus for calcium, 5 plus for phosphorus, and 2 minus for oxygen. And let's do the same thing with the silicon dioxide. No number outside, that means the sum of the oxidation numbers is equals to 0. We don't know the oxidation number of silicon. And we have 2 atoms of oxygen, therefore 2 times the oxidation number of oxygen. Replacing what we know here is that oxidation number of oxygen is -2, and this has to be equals to 0. Therefore, oxidation number of silicon in this case is +4. Then I will write on top of each element the oxidation numbers, +4 and 2 minus for oxygen. The next one is carbon. Carbon is by itself, no charges outside, so that means the oxidation number is 0. And I will write here below the carbon, okay? So element by itself, oxidation number is 0 unless there is a charge outside. Next element is phosphorus. Phosphorus is combined with itself, therefore nobody loses and nobody gains anything, which means oxidation number equals to 0. Moving on, we have here calcium silicate. No number outside, that means the oxidation number, the sum of the oxidation numbers is equals to 0. 1 atom of calcium, oxidation number is always +2 or 2 plus. For silicon is what we want to determine. And here we have 3 times the oxidation number of oxygen, which is -2. Therefore, the oxidation number of silicon in the calcium silicate is going to be, according to my numbers here, +4. So let's write here all the oxidation states. 2 plus for calcium, 4 plus for silicon, and 2 minus for oxygen. And finally, carbon monoxide. Very simple here. Sum is equals to 0. We don't know the oxidation number of carbon, and we know that oxygen is minus 2. There is only one oxygen. Therefore, oxidation number for carbon is plus 2 in the carbon monoxide. So let me write here 2 plus, and oxygen is 2 minus. Okay, looking at the equation and all the different oxidation numbers, we can see here that phosphorus started with an oxidation number equals to 5 plus and moved to an oxidation number equals to 0. If the oxidation number decreased, that means phosphorus gained electrons. Okay? On the other hand, if we look at the carbon, carbon started from 0 and at the end is 2 plus. If the oxidation number increased, that means carbon lost electrons. And that has to make sense. If phosphorus is gaining electrons, someone has to lose electrons, okay? It's an exchange of electrons. And that's always true for a chemical reaction. Now, let me introduce you 4 new concepts. Okay? So let me write here the oxidation numbers that are changing in the process. So carbon is going from 0 to 2 plus or plus 2. That means a loss of electrons. And phosphorus is going from 5 plus to 0. Okay, so that means phosphorus is gaining electrons or electrons were gained. Let's start with the concepts of oxidation and reduction. Oxidation is when an element loses electrons, and reduction is called when an element gains electrons. We have to go back to the reaction and identify who oxidized and who reduced. For this case, the element that oxidized or lost electrons is carbon, okay? Because there is an increase in the oxidation state, and the element that reduced or that gained electrons is phosphorus, because there was a decrease in the oxidation number. Okay? If someone lost electrons, someone has to gain electrons. Now let's introduce 2 more new concepts. called oxidizing agent and reducing agent. Careful here. Oxidizing agent is the compound that causes oxidation. Okay, this is the compound that got reduced. Careful with that. And every time we talk about oxidizing agent, we are considering the whole compound. If oxidizing agent is the compound that got reduced or the element that got reduced, we can see here that calcium phosphate is our oxidizing agent. Okay? In other words, the oxidizing agent will cause another compound to lose electrons, will force other compounds to lose electrons. Every time I'm talking about oxidizing agent, I have to consider the whole compound. And in this case, the reducing agent is the compound that causes reduction, the compound that will lose electrons, and this is the compound that got oxidized. And in this case, the compound that got oxidized is the carbon. Okay, let's put the state here. Carbon solid, and the other one is calcium phosphate solid. Again, oxidation and reduction, that refers only to the elements. Oxidizing agent and reducing agent, that refers to the whole compound. Okay, you have to look who gained and who lost electrons. And knowing the number of electrons that were lost or gained, we can use that to balance reactions. So you don't have to guess numbers. You can use oxidation numbers to balance reactions. So let's see how that works here. So again, we know here that phosphorus started from 5 plus and went all the way to 0. So that means it gained electrons. And carbon started from 0 and lost electrons and went all the way to 2 plus in the products. Okay, so let's write here, lost electrons. The idea here is that the number of electrons lost has to be equals to the number of electrons gained. Electrons cannot be floating in the reaction medium. Okay? Someone has to lose and someone has to gain all the electrons. How we do that to balance the equation? So what I'm going to write here is something called delta. So delta means the change in oxidation state. So let's start with carbon. Carbon started from 0 and went to 2 plus. Therefore, the delta is 2. This number has to be multiplied by the starting number of atoms. We just have one carbon here. Don't need to do anything. And let's do the same thing for phosphorus. We have here that phosphorus started from 5 plus and went all the way to 0. Therefore, the delta is 5. Okay, delta is always going to be positive. However, we have 2 atoms of phosphorus to start with. Therefore, we have to multiply by 2, and that's going to give a delta equals to 10. Now we are going to use the deltas as the stoichiometric coefficient, and it's simply a swap between the delta for the phosphorus will go to the carbon, so we have to have 10, and the delta for the carbon will go for the phosphorus. We have here 2. And that's the starting point to balance the chemical reaction. So to speed up the process here, we are going to have 4 phosphorus on this side. We have to have 4 on the other side. We have 10 carbons on this side. We have to have 10 carbons on the other side. And then, whoops, let's see here. We have 6 calcium atoms on this side. We have to have 6 on the other side. And then we balanced out the silicon. We have 6 silicons on this side. Then we have to have 6 silicons on the other side as well. Okay, so that's how you use oxidation numbers to balance the equations. Okay, doesn't need to be a gas all the time. You can use that, and that will lead you to a start, and from there you just adjust the other numbers. And always remember here that atoms and electrons cannot be created or destructed. They are only rearranged or transferred respectively. If someone is gaining electrons, someone has to lose electrons. Very important here that you know the concepts of oxidation and reduction. We are always talking in this case about elements losing or gaining electrons. And that's completely different from oxidizing agent and reducing agent. And we are talking about the whole compound. Oxidizing agent is the compound that causes oxidation, therefore the one that was reduced. And reducing agent is the compound that causes reduction, therefore the compound that got oxidized. With that being said, we finish chapter number 4, and we will be back on Thursday. I will see part of you this afternoon and the other part tomorrow morning. Okay. Hope you have a good rest of your day.
Thank you.
Bye bye.
Thank you.